Somewhere in a military laboratory in Cambridge, Massachusetts, in 2002, a team of engineers from MIT and the United States Office of Naval Research stared at a small metal pellet resting in a glass container. The pellet was made of aluminum, the same lightweight metal found in soda cans and kitchen foil. When they introduced water to the chamber, something remarkable happened. The metal reacted, releasing hydrogen gas and a surge of heat. No combustion. No ignition. No fossil fuel. Just aluminum and water, and enough energy to power a mid-sized underwater drone for 30 consecutive days at 3 knots. They called it a breakthrough. The world, for the most part, never heard about it. This is not a story about the future. This is a story about something that already exists, something that has existed in various forms for over a century, quietly buried beneath layers of industrial inertia, geopolitical convenience, and the overwhelming momentum of a trillion-dollar petroleum economy. It is the story of aluminum as a fuel. A material so energy-dense, so recyclable, and so shockingly accessible that a meaningful batch of it can be assembled for roughly $12. A fuel that carries no carbon emissions, cannot spill into oceans, does not evaporate from a damaged tank, and can be stored indefinitely without degradation. A fuel that, in the right system, is theoretically inexhaustible, because its only byproduct is the raw material needed to make it again. To understand why aluminum matters as a fuel source, one must first understand how energy itself is stored in matter. Every substance in the universe holds chemical potential energy in the bonds between its atoms. When gasoline burns, it breaks those bonds and releases heat, carbon dioxide, and water vapor. The carbon dioxide escapes into the atmosphere, a one-way transaction that has been slowly destabilizing the climate since the Industrial Revolution. Aluminum behaves differently. When aluminum burns, or reacts with water, it too releases energy and undergoes oxidation. But the byproduct is aluminum oxide, a solid, stable, non-toxic compound that does not vanish into the sky. It sits there, collectible, recyclable, capable of being returned to a smelter and reduced back into pure aluminum using electricity. The loop closes. The fuel comes back. This idea, burning metal as a recyclable energy carrier, sounds like science fiction. But the science is nearly as old as the light bulb. The story begins in 1893, in a German laboratory, where a chemist named Hans Goldschmidt was searching for a method to produce exceptionally pure metals without the contaminating influence of carbon. He experimented with combining aluminum powder and iron oxide, common rust, and discovered something startling. When ignited, the mixture produced temperatures exceeding 2,500 degrees Celsius, hot enough to melt steel in seconds. The reaction was self-sustaining, almost violent in its intensity, and it left behind a pool of liquid iron. Goldschmidt patented the process in 1895. By 1899, it was already being used commercially to weld tram tracks in the city of Essen, Germany. That reaction, aluminum reacting with iron oxide to produce molten iron and aluminum oxide, became known as thermite. And the military was paying close attention. By the First World War, thermite had been weaponized into incendiary bombs. German Zeppelins dropped thermite-based devices over England in 1915, setting fires that water could not extinguish, because thermite carries its own oxygen supply within its chemical structure and does not require air to burn. By the Second World War, thermite grenades had become standard equipment in virtually every major military force. Their primary use was not as offensive weapons but as tools of denial. A soldier could drop a thermite grenade into the barrel of a cannon and render it permanently inoperable in seconds, the molten iron fusing the mechanism shut without the noise of an explosive charge. Thermite was silence made lethal. But the military applications of aluminum energy went far beyond thermite. The Second World War accelerated the development of solid-fuel rockets, and engineers discovered early that aluminum powder, when mixed with an oxidizing compound, burned with extraordinary force. The space race supercharged this research. The solid rocket boosters that would eventually carry the Space Shuttle into orbit burned a mixture of ammonium perchlorate and aluminum powder as their primary fuel, producing approximately 3.3 million pounds of thrust per booster at liftoff. The aluminum was not incidental, it was the heat source. Without the aluminum, the reaction would not have been energetic enough to escape Earth's gravity. All of this was known. All of this was studied. But the connection between military energy technology and civilian fuel systems was almost never made, at least not publicly, and not in a way that changed the infrastructure of the world. The petroleum industry had already won the 20th century. Internal combustion engines, oil pipelines, gasoline stations, refineries, tanker ships. An entire civilization had been built around liquid hydrocarbon fuel, and the momentum of that civilization made alternatives seem impractical even when they were technically viable. Aluminum burned in rockets. Thermite destroyed artillery. Neither was destined for the gas station. Or so it seemed. The turning point, the moment when aluminum began to be seriously reconsidered as a practical fuel, came from two directions simultaneously, one military and one academic, both operating with the same quiet urgency that characterizes research that the mainstream has not yet noticed. On the military side, the challenge was power at the edge. Modern warfare, especially in the era following the September 11th attacks, increasingly relied on unmanned systems. Underwater drones, surveillance vehicles, remote sensors, that needed to operate for extended periods in locations where resupply was impossible or dangerously exposed. Diesel fuel, the backbone of military logistics, was effective but fragile. It could leak, combust unpredictably, and required enormous supply chains that were themselves strategic vulnerabilities. In a 2002 project funded by the Office of Naval Research, engineers at MIT's Lincoln Laboratory began developing what they called an aluminum-fueled power system. The concept was elegant. Aluminum pellets were stored in a sealed compartment. Water, seawater if available, was introduced at a controlled rate. The aluminum reacted with the water, splitting the water molecule and releasing hydrogen gas. The hydrogen was fed into a fuel cell which generated electricity. The byproduct was aluminum oxide, a harmless solid that was simply retained in the vehicle. No combustion. No carbon monoxide. No fire risk. The system was designed to power a mid-sized unmanned underwater vehicle for 30 days, a tenfold increase in range over lithium-ion batteries of comparable size and weight. The energy density of the aluminum fuel was calculated at approximately 84 megajoules per liter, more than twice the volumetric energy density of diesel fuel, and more than 3.5 times that of lithium. A larger version, rated at 3 kilowatts, was prototyped as a portable power supply for forward military bases, a device that could generate electricity silently, from sealed pouches of aluminum pellets and local water, with no fuel convoys required. On the academic side, something equally significant was unfolding at McGill University in Montreal, where a professor of mechanical engineering named Jeffrey Bergthorson had spent over a decade wrestling with the fundamental problem of clean energy transition. Bergthorson had explored biofuels and concluded they could not be produced at sufficient scale. He had studied hydrogen and recognized its fatal flaw, not that it lacked energy, but that it was nearly impossible to transport safely. Hydrogen is the lightest element in the universe, and storing it requires either enormous pressure or cryogenic cooling, both of which are expensive and dangerous. Bergthorson and his team turned to something far more counterintuitive, burning metals directly the way one would burn coal, but with a radical difference. When iron powder or aluminum powder burns in air, the reaction produces a stable solid oxide that falls to the ground. It does not disappear into the atmosphere. It does not create carbon dioxide. It can be swept up, returned to a processing facility, and reduced back to pure metal using renewable electricity, wind power, hydroelectric, or solar. The metal becomes, in Bergthorson's phrase, an infinitely recyclable fuel. He and his team demonstrated that a flame could be stabilized in a flow of suspended metal particles, that it behaved remarkably similarly to a hydrocarbon flame, and that a metal-fueled external combustion engine would have energy and power densities comparable to a conventional gasoline engine. Their 2015 paper in the journal Applied Energy proposed a complete metal fuel cycle, from smelter to engine and back, that would produce zero net carbon emissions. The European Space Agency co-authored the paper. What makes this story stranger and more important is the economics. Aluminum is the most abundant metal in Earth's crust. It is already produced in the millions of tons annually for packaging, construction, aerospace, and electronics. Its price, while fluctuating, is accessible. A kilogram of aluminum powder can be purchased for roughly $8 to $15 depending on grade and quantity. The thermite mixture, aluminum powder combined with iron oxide or rust, can be assembled for even less, with iron oxide itself being so common that it is essentially free in many contexts. $12, the figure that appears in the title of this story, is not a precise scientific claim but rather an approximation of something real, the cost at which meaningful quantities of aluminum-based energetic material can be accessed by ordinary people, without industrial infrastructure, without specialized training, and without the supply chains that make petroleum dependent on geopolitics. That accessibility is, simultaneously, its greatest promise and the reason military establishments approached it with caution. The implications reach further than emergency power for drones or clean energy for power grids. Consider the problem of energy storage at civilizational scale. The central challenge of renewable energy, solar panels in the Sahara, wind farms in the North Sea, hydroelectric dams in Quebec, is not generation but storage and transportation. Sunlight does not produce electricity at night. Wind is intermittent. Hydroelectricity cannot be piped to the other side of the world. What the world needs is a way to store renewable energy in a form that can be transported like a commodity, sold like a barrel of oil, and used on demand. Aluminum is that medium. During periods of excess electricity production, aluminum smelters run their electrolytic reduction process, stripping oxygen from aluminum oxide to produce pure aluminum. The aluminum is shipped in sealed containers like any industrial metal. At the destination, it reacts with water or air to release its stored energy. The aluminum oxide is collected and shipped back. The cycle repeats. No carbon enters the atmosphere. No fuel is consumed except in the initial production of the renewable electricity. This concept has been analyzed by researchers at the Royal Society of Chemistry, who published a techno-economic assessment concluding that aluminum could serve as a viable clean energy carrier to decarbonize remote industries. The electricity consumption of modern aluminum smelting, running on hydropower at the rates found in Quebec, allows the production of aluminum at costs that make it competitive with other energy carriers when the full system cycle is considered. The National Academies of Sciences, Engineering, and Medicine, in their 2021 report on powering the future U.S. Army, dedicated an entire appendix to aluminum fuel, describing it as a potentially practical energy storage mechanism for small-scale, remote, and long-duration operations, noting that U.S. military field manuals had already outlined procedures for producing hydrogen in forward locations using aluminum caustic reactors. And yet, despite all of this, the military research, the academic validation, the economic plausibility, the published roadmaps, aluminum as a mainstream energy carrier remains on the margins. The reasons are structural rather than scientific. The existing energy infrastructure of the world, refineries, pipelines, tankers, gas stations, internal combustion engines, represents trillions of dollars of sunk investment. Transitioning away from that infrastructure requires not just better technology but coordinated political will, regulatory change, and private capital deployment at a scale that no single laboratory breakthrough can catalyze on its own. The aluminum fuel cycle, however technically elegant, requires purpose-built combustion systems, oxide collection infrastructure, and recycling networks that do not yet exist at commercial scale. Bergthorson's team at McGill was still working toward a prototype burner coupled to a working engine as recently as the early 2020s. The MIT aluminum UUV system demonstrated a tenfold range improvement over lithium but remained a laboratory achievement rather than a deployed platform. What history suggests, however, is that this gap between laboratory demonstration and widespread adoption is not permanent. The Thermite reaction was discovered in 1893. By 1915, it was falling from Zeppelins. By the 1940s, every major military in the world carried thermite grenades. Aluminum powder was a component of solid rocket fuel by the mid-20th century. The pattern is consistent. Aluminum-based energy technology moves from curiosity to critical application within decades, not centuries, when the strategic need is sufficiently urgent. The defining strategic need of the 21st century, decarbonization, energy independence, resilience against supply chain disruption, is arguably more urgent than any previous driver. There is something philosophically significant in the image of a small metal pellet reacting silently with water to produce power. No smoke, no explosion, no carbon, just chemistry and energy and a harmless white powder left behind. Aluminum is not a miracle. It is not free energy. It requires electricity to produce, infrastructure to cycle, and engineering to deploy effectively. But it is a material that already exists in extraordinary abundance, that has already demonstrated its energetic properties across a century of military and industrial use, and that has been waiting, as technologies sometimes wait, for the moment when the world is finally ready to ask the right questions. The trick was never inventing the fuel. The trick was always remembering it was there. The military remembered it first, as they usually do, and built submarines and drones around it, and filed the reports in technical annexes and conference proceedings that most people never read. The scientists at McGill and MIT and the European Space Agency remembered it too, and published their papers in journals that reached specialists and were largely invisible to the public. Now, as the consequences of fossil fuel dependence grow more visible and more severe, the question of whether aluminum can scale from military curiosity to civilizational energy carrier is no longer theoretical. The chemistry has always worked. The energy has always been there. $12 worth of powder and a container of water, and more than a century of forgotten history, suggest the answer might already be within reach.